All right. So in this video, we're going to learn how to draw Lewis diagrams. Lewis diagrams are also known as Lewis dot structures. And that's because they are sketches of atoms or molecules that show valence electrons as dots. So we want to write that down. So they're sketches of atoms or molecules that show valence electrons as dots. And it's important to note that it's just the valence electrons that are shown. And the reason is we want to know how valence electrons are involved in bonding, or which valence electrons are bonding electrons and which are non-bonding electrons. Let's look at a few examples. Carbon. How many valence electrons does carbon have? It's in group 14, so it has 4 valence electrons, just like silicon does, so I would draw 4 dots. I'm going to draw them in pairs for reasons that we'll explain later. Here's another example. Sodium. How many valence electrons does sodium have? Well, it's an alkali metal in the first group. Just like all the other alkali metals, it has just 1 valence electron. And something like fluorine, being a halogen, it's in group 17, so it has 7 valence electrons. So I'm kind of drawing them north, west, south, east, just to pair them together and make it easy to see where, for instance, a vacancy exists. Like I'd think about that as a vacancy for an electron in that valence shell. Now, Lewis diagrams, again, are helpful to show how valence electrons are involved in bonding. And we know that there's different types of bonds. And while you can use Lewis diagrams to show ionic bonds, they're more commonly used to show covalent bonds. But we'll start with an example of an ionic bond. You know that, for instance, sodium and fluorine would form an ionic bond quite easily. The sodium atom would just transfer its electron to fluorine, and what we'd be left with is a sodium cation. And so in a Lewis diagram, we put an ion in brackets to indicate that it has an overall charge. And this electron being transferred to fluorine would give fluorine a full valence shell. So that would be a total of 8 valence electrons now. And I'd put a charge outside of the brackets here as well. And that's an example of how we'd use Lewis diagrams to show an ionic compound. But they're really much more helpful to show molecular or covalent compounds. And the example I'll give here, instead of using sodium fluoride, is diatomic fluorine. Now, we want to make sure that we understand the difference between, for instance, a fluorine molecule, which is diatomic, a fluorine atom, which is really a very unstable species, and a fluoride anion. So these are all very different species. And there aren't Lewis diagrams shown here, but I do want to show how the Lewis diagram of the molecule is different from the Lewis diagram of the atom. So for instance, here are 2 fluorine atoms. Just to be clear, that's what this is depicting. I'm going to draw one on the left here with 7 dots. And on the right, I'll draw one with 7 dots as well, only I'll put the vacancy on the opposite side. And on this side of the page, I'm going to draw one diatomic fluorine molecule. And if you can imagine these two fluorine atoms being pushed together until their electron clouds overlap, we know that they can end up sharing those two electrons to get a full valence shell. And before you draw this, I want to stop for a moment and show that typically we're going to replace this shared pair of electrons with a line. So instead of drawing electrons which are shared as two dots, when they're shared, we draw it as a single line. And this was a Lewis diagram for the molecule, for the F2 molecule. And I want to note that single covalent bonds are represented with single lines, where single lines are single covalent bonds. And remember that a covalent bond is two electrons shared. So since there are two electrons shared here, plus another 6 for each fluorine atom, that means each fluorine atom has 8 valence electrons around it in its valence shell, and that's what we call an octet. The next thing we're going to do is introduce these rules for drawing Lewis dot structures. And this handout is an important one for us to use, especially in the beginning. But after a while, with some practice, we won't need to use this handout anymore, and we'll get used to these. So let's just do a few examples. The first example we'll do is that of silicon tetrafluoride. And it's going to be most helpful if you have these rules handy as we go, so you could read the rules that I'm referring to. Silicon tetrafluoride, we know, is a molecular substance, and we learned how to name compounds like that earlier in the year. The first thing we're going to do, according to the rules for drawing Lewis structures, is to count the total number of valence electrons in the atom. So silicon has 4 valence electrons since it's in group 14, and fluorine has 7. 7 taken 4 times is 28. So that's a total of 32 valence electrons that I'm going to need to account for in this molecule. That's step 1 in our rules. The next rules say draw the skeleton of the molecule by connecting outer atoms to the central atoms with single bond. Well, the central atom, it also goes on to say, is the least electronegative. So whichever is furthest away from fluorine, and in this case, that's silicon. And notice there are 4 fluorine atoms which need to be connected to it with single bonds. And we always draw these peripheral atoms radially around the central atom just to minimize electron-electron repulsion. All of these bonds are going to get as far away from each other as they possibly can. And in 2 dimensions, that would be 90 degrees. Notice that to draw this basic skeleton, which is the bare minimum of bonds necessary to keep this whole thing together as a molecule, I would need to use 2, 4, 6, 8 electrons. That means only 24 electrons can be used to complete this Lewis structure. The next rule says to add remaining electrons to the outer atoms in pairs, and I'm going to do that. Specifically, it says to add remaining electrons to the outer atoms in pairs to complete their octets. And an octet, remember, is 8 valence electrons around a nonmetal atom. And the only element that does not need 8, that does not get an octet, is hydrogen, which we'll discuss later. Notice the next few rules, if we read them, are not going to apply here. Rule number 4 says add any remaining electrons to the central atom in pairs. And if you were counting, you'll notice that I used 24 just to do rule 3. And finally, the 5th rule says if the central atom does not have an octet, then you need to try using double or triple bonds. But the central atom does have an octet. 2, 4, 6, 8. We're done. There's the Lewis structure for silicon tetrafluoride. We're going to do a few more before we practice with model kits in a lab. The next one we'll try is nitrogen trifluoride. Pause the video here and see if you can try this on your own. Step number 1 is to add up the total number of valence electrons. Nitrogen has 5, fluorine has 7, so that's going to be a total of 26. Remember, it's just valence electrons that we're counting. Nitrogen is going to be the central atom because it's the least electronegative, and the other 3 atoms are going to be arranged radially around the central atom. So we have already used 2, 4, 6. That means there's 20 left. And if I complete the octets for the outer atoms, that's going to use 18 of them. 2 remain. The next rule says that those 2 go on the central atom in pairs. Now, there is one more rule that says if the central atom does not have an octet, then we need to use double or triple bonds, but you can see the central atom does. 2, 4, 6, 8. Here's the next one we'll try. Oxygen dibromide. Oxygen has 6 valence electrons and bromine has 7. 7 times 2 is 14, so there's 20 valence electrons in this molecule. Oxygen is going to be the central atom because it is the least electronegative. As a matter of fact, that might be kind of hard to know without looking up electronegativity values, so that's okay if you weren't sure which one would be in the middle in this case. Now that I've drawn the basic skeleton, notice I had to use 2, 4 to do that. There's 16 left. And at this point, you might want to realize that using a pencil is going to be a helpful thing to do because occasionally you might need to erase some things in order to finish the rules. You'll notice here I just used 12 to do that. That means there's 4 remaining, and it looks like I don't need an eraser because the 4th step says put remaining electrons in the central atom in pairs, which gives it an octet. And that means that the last rule, number 5, is not needed. Let's look at an example where rule number 5 comes up. The example that I'd like to look at where rule number 5 comes up is diatomic oxygen. Now, this is a little funny for 2 reasons. Number 1, the rule number 5 is going to come up, but also because there are 2 atoms, that means none of them or both of them will be central. So that's 6 times 2 is 12 valence electrons to keep track of. And they're both kind of the central atom. They need to be connected by at least 1 bond, so I'm going to start like that. Out of the 12 valence electrons I have to play with, I have to use 2 at minimum to bond them together. The remaining 10, I'm going to start adding to the outer atoms in pairs, just like rule 3 says. 2, 4, 6, 8, 10, and I'm done. I'm out of electrons. When I say I'm done, I don't mean I'm finished, because the next rule says if the central atom does not have an octet, then we need to try using double or triple bonds. Well, since these are both the central atom, I need to realize that this one does not have an octet. It only has 2, 4, 6. So while I can't just draw another line, I can change these 2 dots to a line. In other words, perhaps these are not non-bonding pairs in O2, perhaps they're bonding pairs. Think about just moving those 2 electrons, or the atom on the left saying, hey, would you mind sharing just a little bit more nicely? And here, by turning those electrons from a lone pair to a shared pair, you can see this oxygen still has 2, 4, 6, 8, and now this one also has 8. I'm going to change this up just ever so slightly to make it a slightly more realistic depiction of where the electrons are by spacing them kind of at 120 degrees from each other so that there are 3 domains of electrons evenly distributed. Remember, electrons don't like each other, and for that reason, they'll tend to be spread out. Try this one before we move on. Pause the video here and see if you can follow along with how I'm going to solve this. So hopefully it made sense there how I had to move electrons around in order to satisfy the octet rule for both atoms. And you'll see, of course, I'm using a bit of white out here instead of an eraser and a pencil, but sometimes you're going to need to erase some things in order to follow those rules when you get to rule 5. So the next thing we're going to do is consider a molecule which contains hydrogen, just to point out this example. And water, of course, is one that you might already know what the shape of it looks like. But let's go ahead and follow the rules for Lewis structure and see what we get. That's going to be a total of 8 valence electrons. The central atom is oxygen, with everything else arranged radially around oxygen. I had to use 2, 4 to do that. There's 4 remaining, and they go on the central atom in pairs. Now, while you might recognize this is a correct Lewis structure, it seems to contradict the shape of a water molecule that you may be familiar with, which is that the water molecule is actually bent. And that's really just a consequence of two-dimensional drawings versus 3 dimensions. This is not an incorrect Lewis structure, nor is it an incorrect drawing. You could just think of it as the top view or the bottom view of the molecule. So be careful. When you're drawing a Lewis diagram, it does not necessarily show you the bond angle. This might look like a 180-degree bond angle, but we'll learn later how to understand why this is a 109.5, or in the case of water, 104.5 degree bond angle. You'll notice that also when I was drawing the Lewis structure for water, I did not put lone pairs on hydrogen. And it's important to remember that hydrogen will never have lone pairs because it does not need an octet. A full valence shell for hydrogen is only 2 electrons. So the last important point I want to make in this video is that hydrogen in a Lewis structure only ever, always, only ever does this. Do not put lone pairs on hydrogen. It will not accommodate them. And that's why hydrogen will never be the central atom of a molecule, regardless of electronegativity, because it can only form one bond. It's never going to have several things radially around it. So hydrogen only ever forms one bond and has no lone pairs. There are many other common bonding patterns that are listed on these rules, and while they are not rules, because there are exceptions to these common bonding patterns are helpful for us to determine whether a Lewis structure is probable. Notice hydrogen only ever forms one bond with no lone pairs. Carbon typically forms 4 bonds with no lone pairs, and there's many different ways to do that. Nitrogen, typically 3 bonds and 1 lone pair. It could be a triple bond and a lone pair, 3 singles and a lone pair, and so on. Oxygen, typically 2 bonds and 2 lone pairs, and halogens, like fluorine and chlorine and iodine, those typically form 1 bond and have 3 lone pairs. So keep these common bonding patterns in mind as you're doing Lewis dot structures.